Hello to everyone. So today we are going to have a fourth lecture on numerical linear algebra and applications. Yes, so let us recall quickly what we did in the previous class. We did what we call a condition number, which will be how the matrices would be get stabilized and what are the ways and means of to get a best approximate solutions. Now today we are going to learn a new thing what we call LU factorization. All of you knowing very well, we wanted to find out a solution to the system A is equal to AX is equal to B. Now the matrix A we wanted to decompose into two matrices L and U, where L is the lower triangular matrix. L is the lower triangular matrix and U is the upper triangular matrix. Lower triangular matrix and upper triangular matrix. We'll see what is the general form of this upper triangular matrix as well as the lower triangular matrix. Before going to that, we would like to have existence and uniqueness of LU factorization. How the matrix A can be written as product of two matrices L and U. So an n by n matrix A has an LU factorization if AK, where k is from 1 to etc. n minus 1, are non-singular. So essentially AII should be free from 0 for I is equal to 1 to n, right? So that means all the leading diagonals should be free from 0 so that we could able to find out the LU factorization. Correct? Well, now having had this definition, we will see some of the examples how the factorization would help us in order to find out a solution to the system AX is equal to B. If the LU factorization exists and A is non-singular, that means the determinant of A should be free from 0. Then we say that the matrix is non-singular. Then the so-called the matrix factorization L into U is unique factorization. That means we cannot have two different L and U when the LU factorization exists and if the matrix A is non-singular. That means the LU factorization is a unique factorization. It's a unique factorization when the matrix A is non-singular. So therefore, the idea of factorizing the matrix A into two matrices LU is that we could able to find out solution to the system in much better way in order to avoid all those difficulties which we do get when you solve the system AX is equal to B. Now let us see the simple example. Example, let's say the first row is 0, 1, the way which I wrote over here. Alright, second row is 1, 0. What is the determinant of this matrix? Determinant of this matrix is, what is the determinant of this matrix? Determinant of the matrix is minus 1. Okay, fine. What about the pivot? A11, that is 0, right? And A22, again it is 0. So that means AKK happens to be 0 for all k is equal to 1 to n. So that means the LU factorization does not exist. Why? Because since the pivot A11 is 0, A22 is 0, so Gaussian elimination scheme cannot be carried out. We will not be able to do any Gaussian elimination for this matrix, right? Okay, what is the remark we learned from this example is, for an LU factorization exists, then the pivots must be different from 0. That means A11 should be free from 0, A22 should be free from 0, A33 should be from 0, etc. Right? So all the pivots should be free from 0 so that we could able to find out LU factorization. Well, there are many more examples how we can able to do it, this LU factorization for a particular example. So I have given very simple example 2 by 2, but one can have even 3 by 3, 4 by 4 and so on, so forth. Let's see how this algorithm works. The algorithm is very simple. You have an input matrix, a square matrix, right? N by n square matrix. That's the input given to you. And what is the output? Upper triangular matrix U, right? Upper triangular matrix U. The multiplicity Mij, this is the multiplicity needed to form the unit lower triangular matrix A is equal to L into U. Now, for k is equal to 1, 2, etc., n minus 1. That means if the matrix is 3 by 3, you should do up to 2. If the matrix is 2 by 2, that means as I spoke earlier, A11 should be free from 0. That means for all k is equal to 1 to n minus 1, now these multipliers Aik is equal to Mik, and this is written as minus of Aik times of 1 over Akk. Or essentially this Akk assumed to be free from 0. So therefore we can form the multipliers Aik is equal to Mik, which will be equivalent to minus of Aik upon Akk, and I is equal to k plus 1, k plus 2, etc. up to n. So therefore this is what is called simple algorithm for the computation of the upper triangular matrix. Now let us quickly recall some of the examples. What are the variants of this matrix? For example, if we have a matrix, let's say A is equal to, let's say matrix is 2, 2, 3 and 4, 5, 6, 1, 2, 4. Yes, this matrix you see here. Right? Now I wanted to see that here, when you are computing the determinant of this matrix, you see 2 times of 5, 6, 2, 4, okay, minus 2 times of 2, 3, minus 2 times of, so this is minus 2 times of, so 4, 6, 1, 4 plus 3 times of, and it is 4, 5, 1, 2. So if you compute over here, so it is 2 times of 20 minus 12, and this is minus 2 times of 16 minus 6, and this is 3 times of 8 minus 5. So you can compute that what would happen to this determinant. Okay, so we could able to find that the lower triangular matrix L and the upper triangular matrix L comma U. Well, so we can able to find out L comma U. Well, let's see the algorithm. That is, we would be forming the multipliers Aik, that is Mik, that is minus Aik, Akk, right? And in continuation to this algorithm, we update the entries of A, right? When you do update the entries of A, that is A is k plus 1 up to n, k plus 1 up to n, okay? Then you do write Aij will be equivalent to the Aij plus the multiplier Mik times of Akj. Then you do the end of this loop, right? Okay. So therefore, we would be able to find out the lower triangular matrix and upper triangular matrix. So therefore, this is very, very important theorem. You see this here. So the every matrix A cannot be decomposed into product of two matrices L and U. There are certain conditions. That is what we learned, the existence of the LU decomposition. That means all the pivots should be free from 0, and the matrix A is non-singular. Then you could able to write the matrix A as the decomposition matrix L and U. Now look at this. What is the remark from this algorithm? What we learned from this algorithm? The algorithm does not give the matrix L exactly. However, it can be formed out of multipliers saved at each step. You see here, the matrix, when you write this matrix A as lower triangular matrix into upper triangular matrix. So obviously the lower triangular matrix can be formed by multipliers. So by using the multipliers, we could able to form the lower triangular matrix. Look at this step. First step you see A of 1. So what is the A of 1 I will have? See, look at this. 2, 2, 3, that is first row. 4, 5, 6, that is second row. 1, 2, 4, that is third row. Now you see here, this is the main diagonal. Below the main diagonal, obviously, they turns out to be 0. How it is 0? You look at here, R2 minus 2R1. Okay? Then R3 minus 1 by 2 R1. So if you apply these two operations, this should be 0, this should be 0. Accordingly, these elements will keep on changes. So it means this is what is the multiplier minus 2. And this is the multiplier that is minus of 1 by 2. So therefore, by using these multipliers, we could able to find out the multipliers. So these multipliers will help us in order to find out a lower triangular matrix. Fine? Yes. So let me go ahead. The second step. So when you go to second step, step 2, A of 2. Look at this, A of 2. So that is 2, 2, 3, 0, 1, 0, 0, 0, 5 by 2. So what is the multiplier over here? Multiplier over here is minus 1. So we would be able to form this, what we call the upper triangular matrix. Upper triangular matrix. And this is the lower triangular matrix. Lower triangular matrix. This is the lower triangular matrix. So these are the multipliers. So by using the multipliers, we would be able to confirm that the lower triangular matrix. You see the determinant of this is free from 0, right? Because all the leading diagonal elements, 1 over here, 1 over here, 1 over here. So these are all non-zero, these are all zeros. We should be able to get the lower triangular matrix. Well, let us go ahead. What is the remark over here? Remark is neither L1 nor its inverse needs to be computed explicitly. That means we don't need to compute the matrix L separately. No need to compute separately. No need to compute separately. So that means you do get multipliers. When you do use all the multipliers, M11, M12, etc., you do get what you call a lower triangular matrix. So therefore, explicitly, there is no need to compute separately. Well, when you do this computation, we also get what we call another important step is how many computations you have made to do this algorithm. That is what is called flop count. So why do you want to have a flop count? So we wanted to have a flop count. We wanted to see the efficiency of the algorithm. Efficiency of the algorithm. So that is in terms of flop count. Step 1. We compute n-1 multipliers and update n-1 to entries of A. That is n-1 square times of entries of A. Each multiplier requires one flop and updating each entry requires 2 flops. So obviously we do have 2 times of n-1 whole square plus n-1 flops. That is floating point operations. Floating point operations per second. That is called flops. Okay, so floating point operations per second. That will give you the efficiency of an algorithm. Well, step 2, computing n minus 1 multipliers and updating n minus 2 raised to power 2 entries requires 2 times of n minus 2 whole square plus n minus 2. That means 2 into n square plus 4 minus 4n plus n minus 2. That means 2n square minus 8n plus n plus 8 minus 2. So essentially it is 2n square minus 7n plus 6. So that means order of n square. So this many for a given input size of the matrix n. So we will have that many flops, floating point operations per second for each count. Well, so we can write it as, we can also write it as, so you can write it as, what is the total flops? You can compute what are the total flops. So now let's, in general, step k requires 2 times of n minus k square plus n minus k flops. Since there are n minus 1 steps, so we will have summation k is equal to 1 to n minus 1, 2 into n minus k whole square plus summation k is equal to 1 to n minus 1 n minus k. So this turns out to be 2n times of n minus 1, 2n minus 1 upon 6 plus n into n minus 1 by 2. So obviously when you do this, it turns out to be 2n cube by 3 plus big O of n square. So that means this many floating point operations you require. Floating point operations. Floating point operations you require. So therefore, the flop count is very helpful in order to find out the efficiency of this algorithm. Now let us look into the difficulties arising in the Gaussian elimination. Let us see, consider the matrix A. So it is 3 rows, 2 columns, right? Number of rows 3, number of columns 2. Fine. Let k is equal to minimum of m comma n, that is 2. That many steps required. So let us apply this algorithm for this matrix. Step 1, m21, that is equivalent to minus 3. That is how it is minus 3. So R2 minus 3 times of R1, so that it will be 0. Then R3 minus 5 times of R1. So this is M31 and this is M21. That is second row, first column. So it is third row, first column. Fine. Now let us look into this. Update the values. So when you update this, A1 of 2 comma 2, that is equal to A22 plus M21 times of A21. So which is turned out to be 2. Fine. So this is 2, got it. Similarly, A32 you want to update it. A32 previous value plus M31. So what is M31? So M31 is minus 5 and A12, that is first row, second column, that is 2. So therefore you do get as 4. That is fine. So these two are computed. Fine. Having said these two things, let us go ahead with the matrix A. Therefore, the matrix A turns out to be A of 1 is nothing but 1, 2, 0 minus 2 and 0 minus 4. That means these two are happens to be 0. So that means you do have only the main diagonal and these are all non-zeros and these are all zeros. That's how you do get the matrix. So when I proceed this step 2, it turns out to be M32 is equal to 0. M32 is equal to minus 2 and A2 of 32 is equal to 0. So I want to update this. So when I update this, I do get as this matrix. You see over here, again this matrix is 1, 2, 0, minus 2, 0, comma 0. That means this is 0 and this is the main diagonal. So everything is 0 over here. So therefore you do get upper triangle matrix. This is the upper triangle matrix. So that is the thing where you have a non-zero and these are all zeros. So 3 by 2 is a upper triangular matrix. So therefore you do get the upper triangle matrix straightforward. Now let us look at into the lower triangular matrix. How you get the lower triangular matrix? By using the multipliers L. So as we spoke, L is nothing but 1 0 0 and this is M multiplied to 1 1 0. This is M3 1, M3 2 and 1. So substitute these multipliers from what we did over there. So you get straight away what you call the lower triangular matrix. Okay. So that means as we see from the previous example and as we also noted down, no need to explicitly compute the lower triangular matrix. So it will be formed just by using what we call multipliers. So let me have a check. So when I have a lower triangular matrix and upper triangular matrix, you see, so 1 1 ja 1, 0 0 0, 1 done. So 3 1 ja 3, 0 3, 5 1 ja 5, 5 correct. So it is 1 into 2, 2, that is 2. 3 into 2, 6, 6 minus 2, that is 4. 5 2 is 10 minus 4, 6. 6 plus 1 into 0, 6. So therefore the matrix is verified. So you could able to write this matrix as the decomposition of two matrices L and U. Okay, let us go further. What are the remarks over here? So the flop count in this case is, turns out to be, you see here, mn square minus n cube by 3. So what is the m in our case? In our case, we wrote this as m is equal to 3, n is equal to 2. So m is equal to 3, n is equal to 2. You see here, m is equal to 3, n is equal to 2. That means the flop count turns out to be flops. It turns out to be, that is 3 times of 4 minus n cube, that is 8 by 3. So that means 12 minus 8 upon 3. So 36 minus 8 by 3, that is equal to 28 by 3. So that means, so around 10. So the 9 is, so 9 plus, so therefore last iteration is 10. So it requires flop count is 10. So in order to execute this algorithm. Suppose if the matrix turns to be square matrix, that means n is equal to m. So what would happen in this case? So n is equal to m means, let's say n is equal to 2. So 2 by 3 times of 8. So therefore 16 by 3. So it is 6 only. So that means if the matrix is a square matrix, so the flop count is turns out to be very low value in compared to the non-square matrix. So this is the observation which we made it from this article. Now let us look at into very quickly what are the difficulties you do get using the Gaussian elimination. Difficulties in Gaussian elimination if you don't do the pivoting. Okay, the first and foremost thing which we can learn from here is Gaussian elimination without pivoting fails if any of the pivots is happen to be 0. For example, A11 is 0 or A22 is 0 or ANN is 0. Any one, if it happens to be 0, because we need to divide with the denominator AII. So if denominator is 0, therefore the value blows up. So therefore, we should make sure that the denominator should be free from 0. However, it is worse if any of the pivot becomes close to 0. So the conclusion is that not just simply it is 0, if it is close to 0, still it doesn't exist, we have a problem. So these are the certain things which we can see it from the Gaussian elimination. So if you don't do the pivoting and there is a threat. Well, having had this discussion, let us go ahead in this direction. Let's see permutation matrix. We do require quite often the permutation matrix because we keep on changing the rows and columns. If a non-zero matrix P has exactly one non-zero row, entry in each row, and one column which is 1 and the rest is 0. So such a matrix which we call it as the permutation matrix. So how this permutation matrix will help us? For example, if I have 0 1 0, right? 0 0 1 or 1 0 0. Look at here. So if you take this column, there is a 1. If you take this column 1, if you take this column 1, If you take this row 1, if you take this row 1, if you take this row 1. So that means it is satisfying the definition of the permutation matrix. So therefore such a matrix is said to be a permutation matrix. Well, how it helpful in the numerical computation? Let's see these examples of permutation matrix. So P1 is 0 1 0 0 0 1 1 0 0. Okay, if you look at this, as we spoke, this is the first column, second column, third column, first row, second row, third row. So it is satisfies. Look at this, 0 1 0 0 0 1 0 0 1 0 1 0. Yes, similarly over here it is a permutation matrix. Over here 1 0 0 0 0 1 0 1 0 1 0 0 0 0 1 0 1 0. So therefore it is fine. So that means the P1, P2, P3 essentially they are all typical examples of the permutation matrix. Now let us go ahead further. Few remarks over here. An important property of a permutation matrix P is that it is orthogonal. So what is orthogonal? P times of P transpose is nothing but an identity matrix. An important property of permutation matrix P is that it is orthogonal. So if the matrix C happens to be orthogonal, what is the speciality of this orthogonal matrix? We will be able to see it in due course of time. Okay, suppose if P transpose is equal to P inverse, that means P inverse is equal to I, right? That is also one category of matrices. So what is the specialty? Transpose happens to be inverse. The inverse of a permutation matrix P is its transpose, and it is also a permutation matrix. So that means the permutation matrix inverse is also a permutation matrix, right? So the inverse of a permutation matrix is nothing but simply P inverse is nothing, P transpose. This is also happens to be a permutation matrix, which we can see from the previous examples. Like when you change the row, look at here. So what happened if you change? So this can be written as 0 1 0 0 0 1 1 0 0. Look at this. So there is a 1, there is a 1, there is a 1. Similarly, it satisfies the definition. So therefore, this is a permutation matrix. Permutation matrix. So therefore, it becomes a permutation matrix, right? Okay, fine. So it is easy for us to define the permutation matrix. Now look at over here, the product of two permutation matrix is a permutation matrix and therefore is orthogonal, right? So as we already spoke, the permutation matrix turns out to be an orthogonal matrix, and if you take the product of two permutation matrix, P into P star, let's say permutation matrix. So again it is a permutation matrix and therefore it is an orthogonal matrix. So if the matrix is orthogonal, then many computations will boil down. We will see in the due course of time how it will helpful to us. So what is a good pivot? As large as possible in magnitude at each step. So we call it as a good pivot. So as we speak and all, good pivot means it doesn't create much problem. So we can divide easily and we try to establish the decomposition easily. That is what we call it as a good pivot. The good pivot, where it occurs, it may be located among the entries in a column, which we call it as partial pivoting, among the entries in a column, this column, this column, this column, this column, or among the entries in a submatrix of the current matrix. That is what is called submatrix of a current matrix, which we call it as complete pivoting. So the good pivot may be located at among the entries in a column. So that is called partial pivoting. So you have all columns, or among all the entries in a submatrix of the current matrix. So the current matrix is nothing but it is a complete matrix. So it can be located at either of these two places, which we call it as partial pivoting and complete pivoting. So in general, we also see that partial pivoting means we will catch hold of the rows, and complete pivoting we also catch hold of the rows as well. Well, let us make one remark over here. The purpose of pivoting is to prevent large growth in the reduced matrices. Okay, what is it's a very common question which comes to our mind. Why do you want to do pivoting? The purpose of pivoting is to prevent large growth in the reduced matrices which can wipe out original data. Right? The purpose of pivoting is to prevent large growth in the reduced matrices. Right? So when you reduce the matrices, if you don't do the pivoting, then it may wipe out the original data. So then original data is wiped out, then you will be in trouble because we are unable to compute the what you call the approximation, best approximation. So therefore the purpose is being lost. So therefore we don't want that. So we wanted to have a pivoting. So one way to do this is keep multipliers less than or equal to 1 in magnitude, and this exactly what is accomplished by pivoting. So what we do is, what the sentence says is, one way to do this is to keep multipliers less than or equal to 1 in magnitude. So in magnitude, we will make it as up to close to 1. That is close to 1. And this is exactly what is accomplished in pivoting. So we do in the pivoting that kind of accomplishment, so that we will be able to get the better approximation. So therefore all that what we need is pivoting is required. If you don't do the pivoting, the original data may be wiped out. So as a result, the error, relative error which we are trying to compute may go up. So which is not a desirable situation. Well, further let's go ahead with Gaussian elimination with partial pivoting. What is this algorithm? How does it look like? How do you compute the partial pivoting? LU factorization using Gaussian elimination with partial pivoting. So what is the input given to you? Input given to you is n by n square matrix. What is the output? An upper triangular matrix U. The permutation indices Rk needed to form the permutation matrix P, and the multipliers Mik needed to form the unit lower triangular matrix L. So as a result, we wanted to write A is equal to L into U by using the permutation matrices, right? So permutation matrices we use it, and series of permutation matrices we use it P1, P2, P3, P4, etc. So that we will be able to write this PA is equal to L into U, where the L is nothing but the lower triangular matrix, and R is nothing but the upper triangular matrix. So therefore, the LU factorization with Gaussian elimination will be very useful in order to find out a solution to the system of equations. Sorry. Now, let us look at into an example. Let's say PA is equal to L into U with row pivoting. So the matrix A is 10, minus 7, 0, minus 3, 2, 6, 5, minus 1, 5. This is the matrix. So obviously the main diagonal, so it is 10, 2, 5, they are all free from 0. That's what I noticed from this. And second thing what I do is, this I wanted to make it as a 0. So what I do is minus 3 by 10 times of R1. I do that. This is what I did over here. Similarly, this one I will make it as, so 5 minus 1 by 2 times of R1. This minus 1 by 2. So that it will be 0. Right? So the corresponding permutation matrix will become an identity matrix. How it becomes identity matrix? You see over here by using this computation. So the previous case you can see over here. M21 minus 3 by 10. M31 is 1 by 2. So already the largest value pivot element is 10, which is the largest among these. You see 10, 5, 10, 2, 5. So among three values, 10 is the largest value. So I pick up the largest value. So the corresponding permutation matrix is an identity matrix. So I do the computation over here. So this becomes, this I take 1, 0, 0, 0, 1, 0, 0, 1, 0. This is the permutation matrix. So this is which I did it. So ultimately I do end up with this kind of matrix, right? So again, this is the upper triangular matrix. Okay. So you can see this matrix also, still you can do some computation and try to arrive in the second permutation matrix. So I want to swap the row 1, 2 and 3. So when I swap the row 2 and 3, so that means this is the matrix and this is the matrix. These are the permutation matrix. So when I swap and all, so I do get this as a multiplier. Minus 1 by 25 is a multiplier and similarly I will have minus 1 by 25 is the multiplier over here. So with these multipliers, so it boils down to, you see this matrix, again this is 1, so this boils down to this matrix. So that means what you do have, this is the one matrix, this is another matrix, this is another matrix, this is another matrix. 4 different matrices you got it. So this is the main diagonal, 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 right? So what we can learn from these matrices is, if you look at very closely, rearranging the above, so we get this matrix, right? So what is this matrix? This matrix is nothing but, you see over here, and this is the main diagonal. So this is the lower triangular matrix and this is the upper triangular matrix. So that means essentially the matrix A can be written as the multiplication of two matrices, lower triangular matrix as well as upper triangular matrix. So therefore this process is very, very useful, because original matrix and we are unable to handle it. We try to decompose the matrix into a lower triangular matrix and upper triangular matrix and see that how the system could be evaluated in order to find out the best approximation. Okay, so let us see another example. Let us look at this example. A is equal to 1, 2, 4, 4, 5, 6, and see this 1, 0, 0, 0, 1, 0, 0, 0, 1. Now apply this R3, R1, swap it. R3 replaced by R1. R3 replaced by R1. So what would happen to the, when you replace R3 by R1? So when you replace R3 by R1, so you do get what we call the multipliers. So what is the multipliers? So M21, the multiplier is nothing but minus 4 by 7, and M31 is minus 1 over 7. These are the multipliers, right? And obviously M32 is equal to minus 1 over 2, right? So when you do this, you do end up with what we call the upper triangular matrix, that is 7, 8, 9, 0, minus 6 by 7, 19 by 7, 0, 0, minus 1 by 2. See that this is the upper triangular matrix. So what is the permutation matrix? Permutation matrix is, this is the permutation matrix which you obtained by using the, so whenever you do the row operations, you keep on do on the permutation matrix also. The updated permutation matrix looks like this. So therefore, ultimately we could write it as P of A is equal to L into U, where U is the upper triangular matrix and L is the lower triangular matrix, U is the coefficient matrix and P is the permutation matrix. So that's how we do the algorithm in case of permutation matrix, right? So today we have learned how the Gaussian elimination can be applied using the partial pivoting, and also we have seen that if you do not do the pivoting, what is the threat we do get? So therefore the original data may be wiped out, which is very rigorous, and we will not be able to get a better solution. So therefore we need to do it Gaussian elimination with partial pivoting. So in the next lecture, we continue the same strategy and how we can able to do the complete pivoting for the linear systems. So with this, I stop over here. So I'm sure that you might have gained the concepts very clearly, and hope that this will enrich your numerical analysis. And in the course of time, we will have some discussions while doing the assignments and all. Thank you very much.